Welcome everybody to our discussion of sequences. So basically, when we think of a sequence, what we actually have is a function. So a sequence is a function whose domain is the set of either positive integers or sometimes we think positive integers and we'll throw in 0. So basically, if we have something like, if we have a sequence 1, 1, 2, 3, 5, 8, 13, 21, and so on and so on, where we see that this is going to be a sequence is that we say that our first element is maybe f sub 1. Our second element, f sub 2. Our third element, f sub 3. So when we say that this is going to be a function, we're really thinking of these subscripts. So the subscripts are really just going to be the index or the domain value. So the index or the domain value of the function. Now, we then just write out our sequence in exactly that form where we don't really pay much attention necessarily to the index or write it in function notation. We just represent things as, with subscripts, as being the third element in the sequence, the fourth element in the sequence. So that we would have f sub 4, f sub 5, f sub 6, and f sub 7, and f sub 8 as elements in our sequence. Now, when we describe sequences, we can really describe them in one of two ways. Okay? The first way is as a recursive form. So the recursive form really is a form in which the value of an element is dependent or given by some function of the previous elements. So for example, if we took the Fibonacci sequence, and the Fibonacci sequence is really generated by, we start off with the first two elements, 1 and 1, and then we get the next element by adding together the two previous elements. So 1 plus 1, so 1 plus 1 is going to go into 2. Then for the next one, we have 2 plus 1 giving 3. Then for the next element, 2 plus 3 gives us 5. 5 plus 3 gives us 8. 8 plus 5 gives us 13. 13 plus 8 then gives us 21, and so on and so on. So this gives us a way of generating a sequence recursively, and if we kind of write out what that would look like, we could say that our nth element of the sequence is given by the element f sub n minus 1, so the element came before it, plus the element that came before that, so n minus 2. And this is going to work for n greater than or equal to 2 or maybe 3, depending on where we actually start. So for n greater than 3, then we're saying that our first two elements, so f sub 1 is 1, and f sub 2 is 1. So that f sub 3 then becomes the sum of the first two elements, and we can describe our sequence recursively in that way. Another sequence that we can define recursively is the arithmetic sequences. Now, arithmetic sequences are kind of generated by, we start off with a sub n, and we take the element that came before it, a sub n minus 1, so the element that came before it, and we add on some number d. Okay, so where this d is just going to be some constant. And so we get a recursive formula that looks something like this, and this will be valid for n greater than or equal to 2 with a 1 given by some fixed number. Okay. And so the arithmetic sequences generate something like that. So for example, if we had, say, a sub n being a sub n minus 1 plus 3, and we say that a1 was 2, what would our sequence look like? Well, we're starting off with 2, and then we would have 2 plus 3. So we had a sequence element 5. Actually, let's switch that order. 2 plus 3 gives us 5, being our 2 plus 3. Then for our next element, we would have 5 plus 3. So that gives us 8. Then for our next element, we would have 8 plus 3, which would give us 11. Then we would have our next element, 11 plus 3, which would give us 14, and so on and so on and so on. And so continuing that sequence, we would have 17, 20, 23, and so on and so on. So arithmetic sequences have this kind of common number that we are adding on to get the next number in the sequence. So a second type of sequence that's pretty common are geometric sequences. So geometric sequences kind of work in the same way, that our a sub n looks like our a sub n minus 1, but now we are going to multiply by some common value r. So we've got r in this case as some constant, and we've got our a1 given by some number. So these are kind of our starting values, and our recursive formula will be good for n greater than or equal to 2. So an example of something like this, if I had a1 was, say, a half, and r equal to 1/3, what would our sequence look like? Well, we had 1/2, and then we would have 1/2 times 1/3, which would give us 1/6. 1/6, so then we would take 1/6 times our factor of 1/3. So that's going to give us 1/18. And if we kind of kept that going from there, we would have 1/54, 1/162, 1/486, and 1/1458. And we could just keep that going, so that for each consecutive term, we're multiplying the one that came before it by our factor of r before it. So we've talked about ways in which we can define sequences recursively. A second way that we may define sequences by something we call a closed form. Okay, so the closed form really just means that the term of the sequence is given by a function of the index. Okay, so for example, we could have something like a sub n be equal to n times n plus 1 over 2. And this will work for n greater than or equal to 1. So now we have our element as a function of n, so that our first term, a1, looks like 1 times 1 plus 1 over 2. So our first term is just going to be 1. Our second term, 2 times 2 plus 1 over 2, which gives us 3. Our next term, a3, looks like 3 times 3 plus 1 over 2. So that's going to give us 6. Our fourth term, which is going to be 4 times 4 plus 1 over 2, is going to give us 10. And we can just kind of keep that going a little bit, for which this sequence we might recognize more terms. We might recognize these as being our triangular numbers. So we had 1, we had 3, we had 6, oops, one too many periods there. So for that one, we had 4, 5, 6, 7, 8, 9, 10 for that one. And so for our next number, we would then have basically the number that came before it, and then we're going to add on another kind of row in this column, or another kind of column in this triangle, rather. And so for that one, now we have 15 for that one. So that our formula in this case, a sub n being n times n plus 1 over 2, we can write this one as closed form. So this is our closed form example of that. But then from this pattern with the triangular numbers, we can also see that, oh, it's possible to write this as in a recursive way as well, that if I would do something like a sub n, I take the triangular number that came before it, and then I add on n. So where in this case, a1 is just going to be 1. And that works for n greater than or equal to 2. And which I see in each one of those cases. Here I have, in my triangular numbers, I have my first element plus 2. I have now my previous triangular number plus 3. I have my previous triangular number plus 4. And then I have my previous triangular number plus 5. And so I can get also either recursive form, or I can get a closed form for my triangular numbers. The same thing can be said even for our arithmetic and geometric sequences. For my arithmetic sequence, remember I described that one as a sub n minus 1 plus this common d that I had. Well, if I kind of look at this, a2 looks like a1 plus d. a3 looks like a2 plus d. But a2 was going to be a1 plus d plus d. So it looks like a1 plus 2 times d. a4 looks like a3 plus d, but a3 was a1 plus 2d plus d. So you get a1 plus 3 times d. a5 is A4 plus D, but that was A1 plus 3D plus D, so that's A1 plus 4D. And if I kind of kept this going, it's pretty obvious that at this point, what does this thing look like? It looks like A1 plus n minus 1 times D. And so this gives me now my closed form for my arithmetic sequences. And if I do the same thing for the geometric, what happens with that? That I had a sub n being a sub n minus 1 times r. Well, if I continue those, so a2 looks like a1 times r, a3 looks like a2 times r, but that is a1 times r times r, so a1 times r squared. A4 looks like A3 times R, so that's going to be A1 times R squared times R, or A1 times R cubed. And if we kind of keep that going, we again see that our geometric sequence is really going to have a form that looks like A1 times R raised to the n minus 1 power. And so that's going to work for n greater than or equal to 1. And so what this gives us is our closed form for geometric sequences. So I hope this has been kind of helpful in describing the different ways in which we can look at sequences, either as closed form or recursive forms. And so coming up in the next video, we'll start looking at maybe problems of finding forms, so finding equations, either recursive form or closed form for a given sequence. So stand by and I'll see you guys in that one.